Okay, so here's problem number 27 from section 4.2. We're asked to find first local extrema. So let's do that by asking some questions. Of this function, are we in a limited domain?
It's plausible.
There we go.
You grab it.
Did you hear what Izzy said? How are we supposed to know? And the
Oh.
answer is by asking these questions. Are there any values that I can't put into x cubed and get a value back out?
No.
No, I can cube any value. Is there any values that I can do negative 2x and not get a value back out? Is there any values in which cosine, you can't put a value in for cosine and get a value out? There are no values here for which these parts of the function aren't defined. So the answer is there are no restrictions on the domain. So our domain is all real numbers. All right? Second thing we're going to do then is we are going to look at the derivative. And I believe this is 3x squared minus 2 plus 2 sine x. Check my calculus, please.
You're good.
We good? And of course, we want to set this equal to 0. Because we're interested in places where the derivative is either undefined, and in this case, there's no place where this derivative is undefined, or places where the derivative is equal to 0. And now, here's the difficulty. You can't solve that symbolically. You cannot find out where the derivative is equal to 0 symbolically. But that's great because we're allowing you to use the appropriate tool.
Finally.
And the appropriate tool is our calculator. Hello, wake up.
I think we should just get Wolf Alpha with these things. That would work a lot better.
Oh, I see. Black.
There we go. All right. Well, I'm sorry. We were doing a little 3D graphing in Calculus 3. Yeah, we're still recording. How come it's not saved? No. Okay. So I'm going to create a. Actually, I'll just go through this in. Okay. So here I am in Sketchpad. I'm going to use the graphing method for finding out the zeros for that equation. I can't remember what the equation was, so let me go to handheld mode only, and I still can't see it.
Oh man.
Move my calculator over here. So I'm going to put this equation in my grapher, and it's going to be 3x
You can't just copy and paste.
squared.
That's really unprofessional.
Well, you know what? Sometimes I am a.
It's not voice activated. Actually, it's pretty cool.
Actually, what I really want is I just want to think it, and then have it happen.
I just want like a servant to enter it in for me.
Sound good.
Follows me around everywhere.
Okay.
That'll be the TI DX.
Okay. So there we are. There is the derivative of the. Sorry. There is the graph of the derivative function. So what can we do with this? Well, we're going to interested in what the zeros are. How would we do that? Menu,
You could also look.
analyze the graph,
0.
find the 0, and then what we do is we set a right bound and a left bound. A lower bound here, and a upper bound there, and there is the location of a 0 for that derivative. That is not enough numbers of accuracy. So I'm going to select it and hit the plus button. And there we go. There we have our 3 decimal places. I'm going to do the same thing again. Menu, analyze, find a 0, lower bound, upper bound. And there is that other 0 that we're needing. And let me add one more decimal place. One more decimal place of accuracy there. All right. And so there we have it. There's the 2 places where the derivative is equal to 0. So these should be the places where there could be a maximum or minimum. Could be. Now, can I take some other things while we have the derivative graph up here for a second? This derivative function is positive when we are to the left of negative 1.123263. That means the original function must be an increasing function because the derivative is positive. Between those two zeros, the derivative function is negative. So that means the function must be decreasing in that interval. And then lastly, we must be having a function that's increasing because the derivative is positive once we get to the right of 0.5594. Now, I'm going to switch this back over to handheld only. And if we have a function that's increasing and hits some point at negative 1.1263, and then the function starts decreasing until we hit some hit the value x is equal to 0.5594, and then it starts increasing again. It sure seems to be whatever value is at negative 1.1263 must be a local max. And the value of the function at 0.5594 must be a local minimum. So there's our part A done. Our part B, I'm going to be probably a little bit more verbose than you probably did in your homework. I'm going to say something like, because f prime of x is greater than 0 on the interval from negative infinity to negative 1.12363, and on the interval from 0.5594 to infinity, because this is where the derivative is strictly greater than 0, and these are the two spots where the derivative was equal to 0.
Got it.
If the function has a positive derivative in these two intervals, then f prime of x is increasing on the intervals from negative infinity to negative 1.1263 closed, and from closed 5594 to positive infinity. And again, it's that weird thing that on the endpoints, the intervals are still considered positive. On the endpoints, the functions are considered to be increasing even though their derivatives are equal to 0.
Yes.
And then that's part B. And then I have to do part C as well. And it's the same idea. Because f prime of x is less than 0 on negative 1.1294 to 0.563 to 0.5594, f of x is decreasing on, almost made the mistake, on closed negative 1.1263 to 0.5594 closed. Yes?
So why is the decrease, why is that closed? I'm still confused on writing my answer.
Okay. Okay. It goes back to the definition of increasing and decreasing that we went with before. Let me make a quick new slide, and let me go through that one more time. Okay, we said by definition that a function is increasing from closed A to closed B if for any x sub 1 and any x sub 2, if where x sub 1 is lower than x sub 2, that there's always x sub 1 to the left hand side and x sub 2 at the right hand side, that f of x sub 1 has to be less than f of x sub 2. Compare these two differences as long as x sub 1 is to the right and f of x sub and x sub 2 is to the left. This is our definition for increasing.
Okay.
That it's got to get bigger further on. So far, so good?
So that is
This is what we said our definition for a
a function increase.
function increasing on an interval.
Okay.
Okay? Now, let's say we have a horizontal tangent there.
Okay.
So the derivative is equal to 0. But could my x sub 1 be right there? And was it true that for any place I put x sub 2, all those values further on are bigger? Yeah, which means that x sub 1 and A is in that interval of increasing. I'm trying to tear apart. It's really helpful to look at the derivative, but our definition of an increasing function is wider than our definition of the derivative being positive.
Okay, but I don't more understand why. Is it a closed interval because those are the endpoints?
Mm-hmm.
And then why, if it's not an endpoint, why would it be a closed interval?
Because our definition of increasing, definition of increasing is consistent with this endpoint being part of the interval of increasing. Okay?
So if it's a closed, that's when it stops increasing?
Yes.
Okay.
So B is a place. Okay, if x sub 2 was B, for any place I could be x sub 1, is the function always less than the value at B?
Yeah.
Okay?
On the interval, yeah.
On this interval. Okay? And so even though there may be a horizontal tangent at B, it's still within the interval of increasing.
Okay.
Okay?
So then after that would be, it would start.
It started decreasing.
It would start decreasing.
If it started decreasing, let's say it goes all the way to C, and there's a horizontal tangent at C, the interval of decreasing goes from closed B to closed C.
And then at C it would start increasing again?
Perhaps.
Because it's a, okay.
Okay.
Okay, thank you.
All right.